Welcome, curious minds, to another deep dive here on AI Paper Podcasts.
Great to be here.
Have you ever dreamt of, well, truly self-improving AI? You know, a system that could learn and evolve without constant human hand-holding.
Or without those massive, meticulously labeled data sets we always seem to need.
Exactly. Well, if you're an AI researcher or maybe an ML engineer looking to stay right on the bleeding edge, you are in for a treat today.
We're diving into a really groundbreaking new technical report.
Yeah, it's from the brilliant minds at Tencent AI Lab, Washington University in St. Louis, and their collaborators.
A strong team.
The paper is provocatively titled R0, Self-Evolving Reasoning LLM from Zero Data.
Zero data, that's the kicker.
Right. Our mission today is to cut through the academic density, give you the critical insights, and show you why this development isn't just about making models incrementally better. It feels like it's about fundamentally changing how they learn.
It really could be a genuine game changer in that respect.
Okay, so let's jump right into that lightning-fast overview. For the next, say, 60 seconds, what's the absolute core idea of R0?
Okay, so R0 aims to smash that data bottleneck we mentioned. It's a fully autonomous framework.
Autonomous how?
It generates its own training data completely from scratch. Zero external data needed.
Wow.
And the ingenious core concept is this. R0 initializes two independent models from a single base LLM.
Okay, two models.
They call them the challenger and the solver. And these models don't just sit there, they co-evolve. They interact in this continuous self-improving loop.
A loop. So the challenger, its job is to propose tasks.
Yes, but not just any tasks. It's specifically rewarded for finding problems that are right at the edge, the boundary of the solver's current capability.
And the solver naturally gets rewarded for mastering these increasingly tough tasks.
Precisely. It creates this perfectly targeted, self-improving curriculum, all generated internally. No pre-existing tasks, no human labels.
And the results, did it actually work?
Oh yeah. The empirical results are quite compelling. R0 substantially improves reasoning capabilities across different LLMs. Well, for instance, models like Qwen 3.4b base saw a boost of over 6.49 points on math reasoning.
That's significant.
And 7.54 points on general domain reasoning benchmarks. So it's not just theory, it delivers real performance gains.
You can even find the code on GitHub if you want to dive in yourself.
That's right, it's open source.
It feels like a really significant leap towards truly self-evolving AI, a scalable path towards superintelligence maybe, by generating, refining, and learning from its own experience.
It definitely points in that direction.
Okay, that's our quick hit. Now let's really get into the nitty-gritty. How did they actually pull this off? The mechanism sounds fascinating. It's the R0 innovation, a co-evolutionary loop. So at the heart of R0, as you said, is this fascinating dance, this kind of symbiotic relationship between the challenger and the solver. It's such a radical departure from the old way, you know, feeding a model tons of pre-made human-labeled data.
Absolutely. This is models teaching each other.
So you start with a base LLM, like something off the shelf.
Exactly. Imagine taking a powerful base LLM, one you might download today. R0 essentially clones it, creating two specialized agents.
Like identical twins who then develop different skills.
That's a good way to put it. The challenger focuses on problem generation, creating new questions or reasoning tasks.
And the solver is there to, well, solve them.
Naturally.
And it's not just a one-time thing. You mentioned this loop.
All right, it's continuous, iterative. The challenger evolves to get better at crafting difficult problems.
More cunning, you could say.
Perhaps. And in turn, the solver evolves to become more capable, rising to meet those new challenges.
So how does this cycle actually play out in practice? Walk us through the steps.
Okay, the process unfolds in phases, like a structured loop. First, the challenger gets trained.
Its goal being?
To generate synthetic questions that are difficult for the current version of the solver. It targets that difficulty sweet spot.
Okay, so it generates the questions. Then what?
Once those questions are generated, R0 constructs a training data set, basically pairs of questions and answers.
Right.
Then the solver's fine-tuned, trained on this new custom-generated data set.
And this whole loop challenger generates. Solver trains, just repeats.
Over and over, allowing both models to progressively improve without any external human input at all.
It's genuinely self-supervised, self-evolving.
It is, like an endless, intelligent feedback mechanism built right in.
The challenger's ingenious training.
Okay, this is where it gets really interesting for me. how does the challenger, know what makes a challenging question all by itself?
Right, that does seem like the magic trick, doesn't it? The secret sauce.
Yeah, how does it avoid just generating nonsense or problems that are way too easy?
It comes down to a very clever reward function. It's built on something called Group Relative Policy Optimization, or GRPO.
GRPO, okay, break that down a bit.
Sure. GRPO is a type of reinforcement learning algorithm. It fine-tunes a policy. LLM basically teaches it to make better decisions, but without needing a separate learned value function, which simplifies things. Think of it like this. Instead of getting an absolute score for a question, it generates.
Yeah.
Its performance is judged relative to other questions it could have generated from the same starting point. It's graded on a curve, essentially.
Ah, I see. Relative advantage.
Exactly. The challenger uses this mechanism to optimize its question generation, to get better at finding those useful, challenging problems.
And you mentioned something about an uncertainty reward. That sounds key.
It absolutely is. They specifically designed this reward to push the challenger towards questions where the solver is maximally uncertain.
Aiming for that sweet spot of difficulty, like 50-50 chance.
Precisely. When the challenger generates a question, the solver tries to answer it multiple times, 10 times in their experiments.
Okay.
The most frequent answer across those 10 attempts becomes what they call the pseudo-label. It's the solver's best guess at the right answer.
Right.
The challenger then gets a higher reward when the solver's empirical accuracy on that specific question is right around 50%.
So it's rewarded for making the solver sweat, but not fail completely.
Exactly. They use a specific formula, 12px 12, which mathematically peaks when the accuracy p is 0.5 or 50%.
That is brilliant. It's like a master teacher who knows exactly how hard to push a student for optimal learning.
That's a perfect analogy. It creates this personalized, dynamically adjusting curriculum.
Are there other parts to the challenger's reward?
Yes, they added some practical elements too for quality control. There's a repetition penalty.
Stop it asking the same thing over and over.
Exactly. It encourages question diversity within a batch. They use BLEU score similarity, a common text comparison metric, to spot and penalize overly similar questions.
Makes sense.
And crucially, there's a format check penalty. This ensures the generated questions are structurally sound, like being properly enclosed in question tags.
So basic hygiene for the data.
Right. If a question fails the format check, bam, 0 reward, instantly discarded. This prevents the system from getting clogged up with malformed inputs. The solver's strategy, learning from the edge.
Okay, so the challenger has cooked up these perfectly calibrated, challenging questions. Now, how does the solver actually learn from them and get smarter?
Right. This brings us to the solver dataset construction phase. It starts with the challenger generating a big pool of candidate questions.
How big?
In their experiments, they used 8,000 candidate questions for each iteration. For every single one of those, the solver tries to answer it 10 times.
10 times again. And the pseudo-label, the sort of correct answer for training, comes from the majority vote of the solver's own 10 answers.
Precisely. The solver is essentially creating its own answer key based on its internal consensus.
That seems potentially noisy.
It can be, and we'll get to that. But here's a crucial step they added to ensure the quality of the training data before the solver learns from it.
Ah, okay. What's that?
They only keep questions where the solver's empirical correctness. How many of its 10 answers match the majority vote falls within an informative band.
An informative band, meaning?
Specifically, if out of those 10 answers, between 3 and 7 answers, match the majority vote pseudo-label, then that question-answer pair is included in the final training set for the solver.
So if it got almost all right or almost all wrong, they ditch it.
Exactly. The formula is P12 and where A chose a threshold. This filtering step effectively removes tasks that are either too easy for the solver, it already knows them, or too hard.
Or maybe just too ambiguous.
That's a key point. If the solver can't even consistently agree with itself on an answer, that question might be ill-posed or genuinely ambiguous.
So filtering isn't just about difficulty tuning, it's also a clever way to ensure the quality and consistency of the self-generated data itself.
Smart. Exactly right. Filtering out those low consistency items significantly improves both the quality and, interestingly, the uncertainty calibration of the training data the solver sees.
Okay, so after filtering, the solver trains on this curated set.
Yes. It's fine-tuned on this high-quality, difficulty-calibrated data set. Again, uses GRPO, but the reward is simpler here.
How so?
It's just a binary reward. 1, if the solver's answer matches the pseudo-label for that question. 0 otherwise.
Got it. So it's rewarded for agreeing with its past consensus on the useful problems.
Precisely. This whole process truly hones the solver's ability to tackle the difficult problems its co-evolving challenger generates, pushing its capabilities higher with each loop. The proof is in the performance. R0's impact.
This all sounds incredibly elegant, almost beautifully self-contained in theory. But, the rubber meets the road with results. Did it actually make these LLMs smarter? More capable in practice?
Well, the results they report are really quite impressive. They definitely seem to confirm the effectiveness of the approach.
What models did they test it on?
They tested R0 across different model architectures and sizes. They used Qwen 3.4b and 8b base models.
Okay.
And also OctoThinker 3b and 8b models, which are interesting because they're continually trained versions starting from Llama 3.1. So different bases, different sizes.
And the benchmarks. You mentioned math and general reasoning. That's key.
Absolutely. Math problems often have objective answers, which fits this framework well. But generalizing that reasoning to broader, more abstract problems is always the bigger challenge, isn't it?
For sure. So how did it do on math?
On mathematical reasoning benchmarks, R0 consistently and substantially improved performance.
Substantially like?
For example, the Qwen 3.8b base model, the larger one, saw its average math score jump by over 5.5 points, specifically plus 5.51 after just 3 iterations of R0.
Wow, that's a solid gain from self-training.
It is, and even the smaller OctoThinker 3b model gained plus 2.68 points, so it shows broad applicability across different model scales.
And you said this was progressive? It got better with each iteration?
Yes, that's right. The charts show the models climbing higher with each R0 iteration. It really underscores the benefit of that co-evolutionary dynamic.
The solver gets a harder, tailored curriculum each time.
Exactly. But what's perhaps even more fascinating is how these improvements generalized.
So even though the challenger was maybe focused on math?
Primarily, yes. Despite the challenger mostly generating math questions in their setup, the model showed significant gains in general domain reasoning benchmarks too.
Like which ones?
Things like NMLU-CRO, SuperGBQA, BBEH, standard tests for broad reasoning.
And the gains there?
The Qwen 3.8b base model, for instance, improved its general domain average score by plus 3.81 points.
That's really interesting. It suggests R0 isn't just teaching specific facts or procedures.
It seems not. It looks like it's enhancing the underlying fundamental reasoning capabilities of the model, which then transfer to other complex tasks. That's the hope, anyway, under the hood. What makes R0 tick?
Okay, so seeing those strong results, I assume they did an ablation study, taking pieces out to see what breaks?
They did, yes. Standard practice, and really important here to understand why it works.
What did they find? Which parts were most critical?
The results pretty much confirmed the importance of each core component we've discussed. The biggest performance drop happened when they disabled the challenger's reinforcement, learning the GRPO part.
So the challenger just generating random hard stuff wasn't enough.
Not nearly as effective. It really showed the critical role of that dynamic, adaptive curriculum generation. Removing the repetition penalty also hurt performance significantly.
Proving that question diversity is essential.
Absolutely. Without it, the challenger would likely just keep generating variations of things the solver already mastered or got stuck on. Stagnation.
Right. And what about that filtering step, where they only kept questions in that informative band for the solver?
That also made a big difference. Disabling task filtering significantly degraded performance, particularly on the general reasoning tasks.
So that highlights its dual purpose again.
Exactly. It calibrates the difficulty, keeping the solver in that optimal learning zone, and it acts as that implicit quality control, weeding out the potentially ambiguous or ill-posed questions.
Training on noisy or poorly defined data just harms robustness, doesn't it?
It really does. You want the learning signal to be as clear as possible, even if it's self-generated.
Okay, this raises that question again, though, the noisy data aspect. If the system is generating its own pseudo-labels via majority vote, how accurate are those labels, especially as the questions get harder?
That is a critical insight from their analysis, and honestly a somewhat surprising finding.
Yeah.
They found that as the challenger generated progressively more difficult questions, and they confirmed the questions were getting harder by testing them against a static, unchanging solver.
Okay, makes sense.
The true accuracy of the self-generated pseudo-labels compared to actual ground truth answers systematically dropped.
Dropped by how much?
It went from an initial accuracy of around 79% in the first iteration down to just 63% by the third iteration.
Wow, that's a pretty significant drop. So the AI is essentially learning from increasingly flawed or noisy data that it created itself.
Yes.
And yet, it's still getting objectively better on the benchmarks. How does that work? It feels counterintuitive.
It does, doesn't it?
Yeah.
And that's a key trade-off and maybe a potential bottleneck for this kind of approach going forward. It needs more research.
But it still worked overall.
Yes, because the framework's internal reward mechanism, the part that drives the challenger, still functioned precisely as designed. The solver consistently achieved around that 50% success rate on the questions generated by its contemporary challenger.
So the challenger was still successfully calibrating the difficulty relative to the solver's current ability, targeting that 50% uncertainty sweet spot.
Exactly. The system is still pushing itself effectively, even if the ground truth it generates becomes less perfect over time.
It suggests maybe the process of being challenged and refining its understanding is more important than having perfectly accurate labels all the time.
That could be one interpretation, yeah. It's a fascinating outcome. The journey might matter more than the destination's perfection, in a sense.
And one last check. What about combining R0 with good old-fashioned human-labeled data? Is it like one or the other, or do they complement each other?
Great question. They found it's not redundant at all. R0 actually acts as a powerful performance amplifier.
How so?
When they took the models already trained with R0, the checkpoints, and then fine-tuned them on human-labeled supervised data, they saw an additional gain of plus 2.35 points on average compared to just fine-tuning the original base model on that same labeled data alone.
Okay, so R0 builds a stronger foundation first.
Precisely. It helps the model leverage that supervised information even more effectively later on, letting it reach performance levels that standard fine-tuning alone couldn't achieve. Outro.
So wrapping this up, what does this all mean for you listening, whether you're a researcher, an engineer, or just fascinated by where AI is heading?
Well, R0 really presents a truly groundbreaking approach to AI training, I think.
It feels like it, a fully autonomous, self-evolving framework
that can learn complex reasoning skills from literally zero external data, just by having this challenger and solver co-evolve and push each other.
It's a really significant step toward overcoming that huge bottleneck of human data dependency, isn't it?
Absolutely. It offers a potentially scalable, maybe even unbounded path towards more general artificial intelligence, or superintelligence, depending on how far it can go.
Though you mentioned it's currently best suited for domains where correctness is objective, like math.
Yes, that's where it shines right now, because determining the pseudo-label accuracy is more straightforward. But the potential implications are still enormous.
Just think about it. An AI system generating its own curriculum, relentlessly pushing itself to the frontier of its own capabilities.
Even if that means creating its own noisy training data along the way.
Yeah, that whole noisy label aspect really challenges our standard notion of what learning even means for an AI.
It does. And it raises that really important question for the future. How far can this kind of self-improvement go in more subjective domains?
Like creative writing or open-ended dialogue.
Exactly, where correctness isn't so clear-cut. How does a challenger push a solver there? What does a pseudo-label even mean?
That's the big unknown.
It is. But this ability of AI to set its own increasingly challenging learning tasks and then learn from them, even with potentially degrading label accuracy, that's a concept really worth mulling over.
Yeah. It hints at a future where AI evolution might just accelerate in ways we're only beginning to grasp.
It could fundamentally change how we design, train, and even interact with intelligent systems down the line. Lots to think about.
Definitely food for thought. Thanks for breaking that down.
My pleasure. Fascinating paper.
Indeed. And thank you all for joining us on AI Paper Podcast. We'll catch you on the next deep dive.